Okay, okay, okay. I think that's fine actually so far. So it's working right now, and we'll start off. Yeah. Okay. Thanks very much, Sagar. Thanks a lot, Santosh. Thanks a lot. Yeah. Okay. Just give me 1 minute. We'll just start. Okay. A very good morning to all of you. I'm extremely sorry for the delayed start today, and I had Zoom problems in the morning, and Santosh and Sagar fortunately were able to help sort it out. Okay. This morning we'll have an overview of the Milky Way. And as normal, feel free to interrupt whenever you have a question. And it'll be largely qualitative. It's towards the end of the school, and I don't want to load you with too much of either information or mathematics right now. Okay. What the picture shows you over here is a view of the Milky Way as seen from the southern hemisphere. Not only from the southern hemisphere, this is as seen by the indigenous Australians. And what you see at the bottom is a cave, is a stone carving of what they saw as an emu in the sky. In late autumn, this is the time when the emu lays their eggs, and the eggs were also a source of for the indigenous communities. The ancients were far more intimately related to the sky than we are today in modern times. They relied on the heavens for the seasons, for directions, and there were lots of myths and legends in different societies or different civilizations regarding what they saw in the heavens. But although, for example, in most Western civilizations, Greeks, Indians, etc., and Indians as well, the myths and legends are centered around the stars. But you will find that when you come to the indigenous Australians, a lot of their myths and legends were also woven around the dark spots which they saw in the sky. Here, for example, the dark spot near the Southern Cross over here was the emu's head. This is the emu's neck. And this was aligned. This photograph was taken when this part of the sky appeared above this cave sculpture or cave drawing which the Aboriginal Indians made. So you can see that this is a picture which was taken by Barnaby Norris, who's the son and collaborator of a friend Ray Norris, and he had got the Eureka Prize for it in 2007. Beautifully rendered, taking lots of shots together. So before going further into the scientific aspects of it, I will also tell you a little bit of the historical context in which we have come to understand our galaxy, our home galaxy, the Milky Way. Now, here are pictures again of the Milky Way as seen from Paranal Observatory in Chile. And these are the satellites of a nearby town. You can see the large and the small Magellanic clouds over here. And what you see in the optical light are not only diffuse patches of light, but as we just saw, dark patches as well. Okay, dark patches as well. And this laser beam over here points to where the center of our galaxy is. And it is shrouded in dark regions, as you can see, but also there are diffuse lights around it. And we shall try to understand how these structures arise. What is the basic structure of our galaxy, which itself is an interesting story because we are sitting inside it. When we are looking at the heavens and we see a galaxy either edge on or face on, it is easier to discern the structure of the galaxy. But when it comes to sitting inside it and you're surrounded and you cannot see very far, then it becomes quite an interesting story to try and find out what is the actual shape of our galaxy, what are the various structures that lie around it. Now, I'll keep asking you questions as well, and you're welcome to ask me questions as well. Okay. Now, can any one of you just unmute yourself and tell me why you see the dark patches in the sky over here in the Milky Way? And you can put it in the chat, or you can
Is it due to interstellar dust?
interstellar dust. Very good, sure. Okay, interstellar dust, which absorbs the starlight from behind it. Okay, and that is what is responsible for the dark patches which you see. Where these dark patches lie, we will try and have a better look as we go along. Okay. Now, just a little bit of history, as I said earlier. Initially, right in the early days, till about the NASA period, actually, we were wondering whether our galaxy was the entire universe, or is it one of many such galaxies in the universe. And the Milky Way comes from the Latin word via lactea, because we could see it's a diffuse, white patch of light, or very light white in the night sky. It is also referred to as the Silver River in Chinese and East Asian languages. The tribes in the nomadic Saharan region used to call it the backbone of the night. And as you will well imagine, that ancient astronomers would not have been able to resolve stars. And but although they were not able to resolve stars, the atomist philosopher Democritus, who talked about atoms by breaking an element up into smaller and smaller bits, speculated that the bright bands which you see may indeed consist of distant stars. But during these ancient times, Aristotelian cosmology prevailed. He had a very dominating influence, and he interpreted this diffuse patch of light as a contact between the celestial and the terrestrial spheres. It was left up to Galileo, 16th century or so, to resolve the stars in the Milky Way with his telescope, which he sort of wrote in great detail in the Sidereus Nuncius, which was published in the 17th century, 1610 Common Era. So you can see that our galaxy has been the realm of speculation in ancient times, and it is only with observations that one is slowly began to realize what it consisted of. But it took many more steps to try and find out whether our galaxy was the entire universe, or was it part of, or was it just one galaxy among millions of such galaxies. The Magellanic Clouds, which I pointed out earlier when I showed you the picture of the Milky Way, which are our two dearest neighbors. They were named after Magellan. His historian Pigafetta had recorded it for the Western world, but these were, of course, known to indigenous Australians much before, much before, thousands and thousands of years before Magellan made his voyage. And among diffuse clouds of gas, it was Al-Rahman al-Sufi who observed a small cloud towards Andromeda, and that was in 964 Common Era, and that is the Andromeda Nebula. He published his book, A Book of Fixed Stars, in 964 Common Era, and this is a beautiful illustration of Sagittarius, along with a beautiful calligraphy which you can see. At that time, of course, we didn't know what Andromeda was, that it was an independent galaxy, but it is probably one of the very early records of a galaxy, besides the Magellanic Clouds, although the natures were not known at that time, of galaxies outside our own galaxy. This is our immediate neighborhood. But these such diffuse nebulae were catalogued, were listed by Charles Messier. Charles Messier was really interested in looking at comets, but he didn't want to be confused by diffuse objects in the sky, and he made a list of objects which should not confuse him with comets. Many of them are galaxies like our own, but there are all kinds of diffuse nebulae over there. For example, supernova remnants, globular clusters, elliptical galaxies, spiral galaxies, nebulae. They all make up his list of diffuse objects, not to be confused with the comets that he was looking for. His initial list was a slightly smaller list, but several objects were added later by astronomers who went through his list, and there are 110 objects, as you can see, listed over there. These are among the most beautiful objects in the universe because they're relatively nearby. M1, the Crab Nebula, M87, elliptical galaxy, where the Event Horizon Telescope mapped the black hole. We can see the Trifid Nebula over there, Ring Nebula over there. So there are a whole lot of galaxies as well as nebulae within our own galaxy, which are catalogued by Charles Messier. Now back to our story of the Milky Way. And as I said earlier, these names came from Latin and Silver River Chinese and East Asian languages, backbone of the desert from the Kalahari region. And it was the English astronomer Thomas Wright, who was a very versatile person, polymath in many ways, furniture designer, gardener, mathematician, philosopher. And he published an original theory or new hypothesis of the universe. And he speculated Milky Way was a flat layer of stars. Our solar system is a part of the Milky Way. And he speculated that very faint nebulae, in all likelihood, may be external creation bordering upon the unknown and too remote for our telescopes to reach. Okay, so this is one of the very early speculations that our Milky Way is not alone, and it is just one of many other galaxies. And this was further sort of taken forward by Immanuel Kant, the philosopher and contemporary, and referred to these faint nebulae as island universes. But to make further progress, you need to make observations. Observations which link up to, in those days, largely speculation, but today we know that it's theoretical models and observations which go together to make the advances in our understanding of the universe in most sciences as well, in sciences as well. Now, William Herschel, a refugee musician from Hanover who became the astronomer royal, he built some of the most powerful telescopes of his time, and he began to count stars, some of the very early work on stellar counts. And by counting the stars in different distances, he tried to find out the shape of the Milky Way from star counts. He found stars to be denser in one direction than the other, and he found the sun located near the center of the Milky Way. Herschel observed about 600 different locations, and he counted every star, assuming stars were similar. We were still not at the age when the Hertzsprung-Russell diagram was known, and he made a simplified assumption that all stars would be similar, so that the fainter stars are further away. Today we know that stars have a luminosity distribution from the very faint or less luminous stars to the most luminous O and beta stars to those which are red, very low luminosity stars. But at that time, when he was trying to find out the size of the universe or the scale of the universe or the shape of the universe, he tried to find out by assuming that the fainter stars were indeed further away, and came across this and suggested this model of our galaxy. This was taken a bit further by Jacobus Kapteyn, who collected photographic plates from different parts of the world to construct a model of the Milky Way. So as you can see that his scale was larger. It's a flattened system with a radius of about 8,500 parsec. And as you well know by now, that one parsec is about 3.26 light years. But in both the models, the sun is offset from the center, but is still close to the center of the galaxy. Okay. Now, can you sort of speculate from what you have learned so far as to why in these models the sun appeared to be at the center of the galaxy? You can put it on the chat, or you can unmute yourself and speak, whatever you find convenient. You can see that both in Kapteyn's universe, okay, all right, and also in Herschel's universe, the sun was not exactly at the center, but roughly at the center of the galaxy as they saw it. Today we know that it is 8.5 kiloparsec away roughly, in a pretty nondescript part of our galaxy, in the Orion, close to the Orion arm. But why do you think that Herschel and Kapteyn, when their observations were made, found the sun to be very close to the center of the galaxy, as they saw the galaxy to be? Think a little bit. Any suggestions? No? You can put it in the chat or you can speak. No? Okay. Nobody? Okay. Okay, think for a moment. For example, suppose you had suppose you had lots of friends playing in a school playground. Okay, playing in a school playground. and suppose they were not symmetrically distributed. Okay, and you were at one end of it, say one, not exactly at the end, but say one third away from it. All right. Now, if you could see everyone over there, then you would say that you were one third away from where you're supposed to be because you can see all your friends in the field. But suppose you could see only till about 20% of the distance. Okay, 20% of the distance, and they were all uniformly distributed in that region. Then you might say, because suppose there is a fog in the field and you can only see a certain distance, then you will say that okay, I'm at the center because you see equal numbers all around you. So similarly, because of the interstellar medium of the galaxy, which you know about, and which you correctly said is responsible, the dust and gas is responsible for the dark spots which you see, that you will only count stars till a very limited distance from you. And within that limited distance, you will know that you know today that that you can count stars towards the center as well as the anti-center. So there will be a difference in the density of stars depending upon which direction you're looking at. And then you will find yourself close to the center of the galaxy, the center of what you're counting, because you are not being able to see very far away. So dust, you can see, manifests itself in very different ways, and these were the early pictures of uh, of what a galaxy might look like. The major step which was taken was by Harlow Shapley. Now you know about globular clusters, but I'll tell you a little bit more about it. Globular clusters can contain thousands and tens of thousands of stars. They're very bright objects, and due to the work of Henrietta Leavitt and others, we are able to measure distances. We were able to measure distances to globular clusters. And what Harlow Shapley did was that he used globular clusters to get a better idea of the structure of the Milky Way. Globular clusters are bright, they are big, and as you shall see, they're not confined to the plane of the galaxy also. So you can see them to large distances. So once you measure the distances to the globular clusters, what Harlow Shapley did in 1917 was that he plotted them in a coordinate system where you can see this gray shaded area is the plane of the galaxy. The zero, which is over here, and the zero, which is over here, marks where the sun is located. Okay, uh, you're unmuted. Can you mute yourself, please? Otherwise, I'll mute you. All right. Don't unmute yourself unless you are speaking because you pick up a lot of background noise and disturb everybody else. All right. If you're speaking, please unmute, but otherwise don't unmute. Okay. So you can see the sun is over here at 00. This is about 20 kiloparsecs. Okay. And this is about 5. This is 10. So he saw that the globular clusters were centered not on the sun. The globular clusters were centered, he suggested, around the center of the galaxy, which placed it at about 8 kiloparsecs away. So as I mentioned, the shaded region is the plane of the galaxy, and the globular clusters have a spherical distribution. Shapley, of course, at that point of time, we didn't know the widespread prevalence of dust. So he overestimated the distances because the objects, the further objects, would appear sort of fainter because of extinction by the dust itself, in addition to the inverse square law of distance. Okay. But he got the picture right that we are not at the center of the galaxy because the globular clusters, which are more or less spherically distributed, were at the center of our galaxy. So we are getting a better picture now by looking at the distribution of more luminous objects and being able to see further than what Herschel and Kapteyn were able to do to try and reconstruct the structure of our galaxy. So there is a point on the chat. Let me see what it is. How do we come to know the shape of the Milky Way? That will come to in a very short while. Okay, that will come to in a short while. Okay. So right now, but basically it is by looking at the distribution of the stellar and the gaseous components of the galaxy that we come to know what the shape of the Milky Way is. But we'll look at it in a bit more detail in a short while. Okay. Now, so we've come so far that we know that the center of the galaxy is about roughly 8 kiloparsec away by looking at the distribution of globular clusters, which are spherically distributed about the galactic center. But is our galaxy the entire universe? This was something which was not settled uh, even after that. And there was a very famous debate called the scale of the universe in 1920 between Shapley, who suggested the spiral nebulae which we see were within our galaxy, versus Herbert Curtis, who said the spiral nebulae are island universes, using the phrase of Immanuel Kant, the philosopher, and far outside the Milky Way. Shapley relied on the observations of a galaxy called the Pinwheel Galaxy by Van Manen, and he reported evidence of the galaxy rotating. Now, Shapley argued that if galaxy is rotating, and if it is at a distances at which much further from our galaxy, then this galaxy would have to be rotating extremely rapidly, and which is probably untellable. So he tried to argue that the spiral nebulae were within our galaxy. But today we know that Van Manen's observations were not correct, and the spiral nebulae are indeed outside our galaxy. But how did we actually establish that in the very early days? That was left to Edwin Hubble. So I mentioned about CFITs a little while earlier. You must have learned about CFIT variables in the course of the summer school and refresher course. They're variable stars at a regular period, and Henrietta Leavitt, when she first studied the Magellanic Cloud, found that the period of variability of the CFITs was related to the magnitude, and later, once we measure the distances, we know that there is a well-calibrated relationship between the variability period of these stars called CFIT variables and the luminosity of the star. So all you need to do is to be able to identify a CFIT variable, monitor it. Once you monitor it, you know the luminosity of it from the calibrated period luminosity relationship. And once you know the luminosity and you know the observed flux, you can estimate its distance. So Hubble, what he did was he identified CFITs in the Andromeda Nebula and showed that it is well outside our galaxy, a distance of about 2.5 million light years, of about 770 kiloparsecs or so. And we know that the Andromeda Nebula is approaching us at roughly minus 300 kilometers per second, and will collide with the Milky Way in about 4 to 5 billion years or so. Now, although the universe is expanding, as you have learned, that there are random motions within groups, and the Andromeda Nebula is approaching us because of the random motions due to the gravitational influences of galaxies within the group itself. So today we know that these spiral nebulae are within our galaxy, and we have taken the steps towards identifying uh, the center of our galaxy as well as the scale of the galaxy. You asked about sizes, the precise shapes. We'll come to that in a little while. Now, this is an image of a galaxy which has been put together by lots of photographs taken by Axel Mellinger. It's an all-sky panorama, and you can see the dark spots, which you all correctly mentioned, is due to obscuration of starlight by gas and dust. And you can see the plane of the Milky Way. This is plotted in galactic coordinates, where the equator is a galactic plane, and this is the north towards the north of the galaxy plane. This is the south of the galactic plane, and these are the two Magellanic clouds: a large Magellanic cloud and a small Magellanic cloud. Now, I will ask you two questions. One is, what do you think the galaxy would look like at longer wavelengths? And also, I'm going to ask you to guess or give a number on what fraction of volume of the galaxy you think is occupied by stars. Okay, but first, let me ask you, what do you think the galaxy would look like if I looked at it at longer wavelengths? Let me go step by step. First, let's look at it at long infrared wavelengths. What do you think the galaxy would look like? Would it look like exactly the optical wavelengths, or would it look different? And if it looks different, then why is it different? And if it looks the same, why is it the same? So you can unmute yourself and or put in the chat box, whatever you like. So whatever you've said so far, you have to stitch together what you know to answer this question. It's a very simple question. Very good. There is one input in the chat. It should look red. Dust region will be brighter. Okay. it should look red. Dust region would be brighter. Okay, we'll any other inputs you want to uh, say anything more? Red, Bharti Patil. Okay, 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 okay. Let's see what it looks like. Okay, now you'll find a lot of the images which you see are false color images. Okay, this one I think is probably a true color image, but color is something which we perceive with our eyes. Okay, for example, when you even today when you make images with CCDs, the CCDs, the electrons don't have color. So it's a lot of image processing which is required to make an image which will give you the colors which you perceive with the eyes. Our eyes are recognize colors, but that is not true of other wavelengths because we see at the optical wavelengths. And also when you make images with telescope, particularly with modern day detectors, they don't give you, I mean, with detectors, they don't give you color images. That is done with a lot of post processing to mimic what you would see with your eyes. Now, all your answers are in the right direction. For example, just as the long wavelength light will come through, but it depends on the degree of obscuration which you see. So if you move slightly towards longer wavelengths, you'll see a little bit of the red light coming through from the dust. But what happens when you look at it at the far infrared wavelengths? This is false color, by the way. Okay, that you will see that there are two things which will happen. One is that you'll see emission from the dust itself, and the other thing is that you'll see all the background stars as well, depending upon the wavelength that you're operating in, because it is the small wavelength radiation that will scatter much more, just like sunrise and sunset or something up in the sky. The basic physics is very similar. So you don't see the dark regions in the galactic plane. So your answers were in the right direction. And but it need not be red. It depends on the wavelength of radiation. But many of these dark globules, for example, the Bok globules, very dark clouds, when you go to longer wavelengths, you can see some of the stars looking very reddish, reddish because the long wavelength red light has come through. But generally there'll be emission from the dust itself, as well as far less obscuration or very little obscuration from the gas clouds of the background stars because you're operating at long wavelengths. And there would be a lot of these old stars which you will see at longer wavelengths because you've studied well by now that the temperatures are given by lambda and T equal to constant, the Wien's displacement law, because the continuum spectrum can be approximated reasonably well for stars by a black body spectrum, so that when you're looking at longer wavelengths, you're looking at the low temperature stars. Okay, and that'll also sort of dominate. There are many more low mass stars and low luminosity stars than high mass stars or high luminosity stars. Now, to the second question which I had set out, what fraction of volume is occupied by the stars? What do you think? I mean, you can see billions of stars exist in the galaxy, and you can see in this image that there's no dirt of stars. The diffuse patches of light are also resolved into stars when you look at it at a telescope. So, what fraction of volume do you think is occupied by the stars? You can give it as a percentage. So, what do you think? So, there is a number in the chat. So, there are two things in the chat. 0.99% it says. 0.99%. Okay, so that is roughly 1% of volume occupied by stars. Vidya says 1%. So, so a few more answers. About 4 to 5%. Disha says. Hariharan says 5%. So we are now between 1 and 5%. Atanu says 5%. Subrata says 4 to 5%, 5%. So all of you seem to 7%. Amit Kumar has gone up a little bit to 7%. So 1 and 7%. So any more answers? I will wait for 10 or 15 seconds at the most. So far, we have gone between 1 and 7%. No more answers? Okay. So let's see. Okay, 5%. So the overwhelming consensus seems to be 5%. There was 1%, and Amit Kumar has gone a bit higher to say 7%. So let's see how would we get just a rough number. Okay, and you can make an estimate from the total number of stars, and you can calculate the volume. But just to get a very rough number, okay, very rough number. It will also vary from location, where you're in the galaxy, where you're in the galaxy, whether you're in a spiral arm, interarm, whether in the bulge, and so it'll and how far away you're from the center. There will be variations, but let me just give you a very very rough idea. To get a very rough idea, what I will do is that I will calculate the fraction of volume which is occupied by the sun, okay, in its local neighborhood. Local neighborhood. So what will I do? I will try and take the distance to the nearest star. So nearest star is Proxima Centauri, which is part of the Alpha Centauri system. Okay. And you know the radius of the sun, which is 700,000 kilometers, so 6.96 in the power of 5 kilometers, and distance to Proxima Centauri, okay, which is a very faint star in the Alpha Centauri group, which is about 4 into 10 to the power of 13 kilometers. So if I did a ratio of the volumes, I get a minuscule number, 5 into 10 to the power of minus 24. Okay. Now, to get a perception of what that means, let's take a 100-kilometer distance. 100-kilometer distance, if you convert it to millimeters, it should be 10 to the power of 8. Okay. I think it should be 10 to the power of 8, right? 100 kilometers, that's 1,000 meters. There's 5, 6, 7 would be centimeters, and another 10 would be millimeters. So 10 to the power of 8 millimeters. If I cube it for the volume, it will be 10 to the power of 24. It is of that order. So it is like a grain of sand, you know, in a 100-kilometer volume radius. So if I'm in Bombay right now, some of you are in Pune maybe. So if I had a grain of sand in Bombay, the volume which would be empty would be till Pune. Okay. So you can see that it's a very, very, very tiny, minuscule amount of volume which is occupied by the stars. It's not 5% or 1% or 7%. It's absolutely minuscule. But the stars, of course, contain almost all the mass, most of the mass of the galaxy, but the fraction of volume it occupies is very small. So if two galaxies actually collided and only consisted of stars, there would be some tidal effect, gravitational influence of the stars on one another, but they could almost pass through. A lot of the bizarre or exciting things which you see is because the space between the stars is not empty, but it consists of the interstellar medium. I will not delve much into the interstellar medium, but just briefly introduce you because Sri Anand is going to talk to you about great lengths about diffuse gas, diffuse matter in space. But you can see that the space between the stars, which you mentioned earlier about gas and dust, fills up the volume, right? And the stars occupy a very small volume of in our galaxy, and that is true of other galaxies as well. So the medium between the galaxies is what we refer to as the interstellar medium. This is a sort of table which I took from Malcolm Longyear's book, a very excellent book on high energy astrophysics, and it consists of different components. It consists of molecular clouds, which are the densest components, greater than 10 to the power of 9 particles per meter cubed. Fraction by mass is 40%, but it occupies a very small fraction of the volume. And these are the cold regions, 10 to, power 10 to 30 Kelvin. And these are the regions where, because they're cold and they're dense, they can collapse to form stars. All right. So we'll not digress into that, but it's something you should know. And as I go up, lower down this table, I'll find gas which are less dense, okay, occupy greater volume, and they're less dense and they're higher in temperature. These consist of molecular lines, dust emission by which you detect them. Carbon monoxide is one of the very well-known lines by which you can easily detect these molecular clouds at radio frequencies. And the diffuse clouds via the H1 21 centimeter emission and absorption, which you know is the spin flip transition with the electron and the proton spins being aligned or misaligned. Then comes what is called the intercloud medium. Different words are used also: cold neutral medium, warm ionized medium, etc. But these are the broad categories of it. And here, hydrogen begins to get ionized. There are free electrons. Ionization fraction is about 10 to 20%. The volume increases dramatically. Mass decreases. Density decreases. Temperature increases. Then you have the hot coronal gas, which is highly ionized. In fact, you can detect them in soft X-rays. Lines in the X-ray region occupies the highest fraction by volume and lowest fraction by mass. Number densities are lowest and temperatures are the highest. And what you'll notice is that very roughly, you can see that these different components are in rough pressure equilibrium. If you just do NT, in the rough ballpark, you'll find it. But molecular clouds themselves also have structures. Within them, they're not just homogeneous clouds, but that is something we will not digress into today. So now today we have a galaxy which we know, which we'll see is a spiral galaxy, but we have seen it is a center. It has a center which we have identified. It consists of stars which occupy a very small fraction of the volume, but accounts for most of the mass, and the space between the stars is filled with the interstellar medium of the galaxy. Now let's look at a bit more detail into the galaxy itself. So this is the bulge of the galaxy. Okay, all the spiral galaxy generally they have a bulge, which looks very much like an elliptical galaxy. And in addition to that, this is an edge-on view. You have the spiral arms, you have the stars and gas over there. Okay, so this is referred to as a disk of the galaxy. And then you have the globular clusters, which you mentioned earlier a little while ago. And globular clusters swarm around the disk of the galaxy. And so the three main components which are being highlighted over here is a bulge in the center, and right in the center of the bulge is the center of our galaxy. Then you have the disk, and then you have the halo. Okay, the halo consists of whole stars in the bulge, halo, and globular clusters as well. So some of these stars may have formed when the galaxy itself formed. For example, when a gas cloud has collapsed to form this galaxy originally, some of it could have condensed to form stars. So that these are sort of old stars which are there in the bulge of the galaxy. Then there are also cases or examples where these stars may have formed by nearby galaxies which have been ripped apart by the gravitational potential of our galaxy. If you look at our galaxy, or almost all galaxies, they're not isolated. They have their own sort of companions. They are in groups, and these groups these galaxies interact with one another. Bigger galaxies may swallow up smaller galaxies, may tidally strip them. And if you have a dwarf galaxy which is sort of orbiting our Milky Way, it could be gravitationally, tidally stripped apart. And some of the stars from these dwarf galaxies could also be a part of the halo. Sorry, you were saying somebody was saying.
रिक्वेस्ट लेटर देते माझा एरियल काढा आणि वन टाइम माझा डिटेल्स भरून चलो बाय.
Okay, somebody had unmuted, so I couldn't follow if it was a question, but I'll move on. If it is a question, repeat it later. But please keep your mics muted.
Bye.
I request all of you to keep your mic muted, otherwise I'll have to just mute everybody. Okay? All right. Let me see what the chat says is. Yeah. Subrat is asking all to mute their mute your audios. Yeah. Please be considerate to others and mute your audios. All right?
income tax
Sagar, it may be best to mute everybody, because the thing is that the people who are making it unmuted, and I will ask people to put their hands up, and if they put their hands up, I will unmute them. Okay? Thanks a lot. Okay. Okay, Subrata, your mic was unmuted, I think, right? So please be responsible and mute your mics. Okay. Now, where was I? Okay, I talked about the three main components of our galaxy: the halo, the bulge, and the disk. Okay. Now let me just have a look at the time so that I am keeping to schedule. Okay, let's see where we are. Okay, I'll probably take about 10 or 15 or 20 minutes more, and I'll go a little bit more rapidly, right? Okay. Right. Okay. Now, I'll just tell you a little bit. I've introduced the term population 1 and population 2 stars. The population 1 stars are metal rich. They are in the disk of the galaxy. And metals, astronomers, as you know, refer to anything heavier than hydrogen and helium as metals. They're found primarily in the disks or spiral arms. They orbit about the center of the galaxy, both young and about the center of the galaxy. And they consist of both young and old stars. The old stars could be up to about 10 billion years old or so. And examples are young stars in Orion, and the sun itself is also metal poor. So it looks at the abundance of, say, iron, for example, to hydrogen, and below a certain threshold, it will be called metal poor, and above a certain threshold, it will be called metal rich. Metal poor stars are found in the bulge halo disk of our galaxy, and they're old stars formed very early in the evolution of the universe. The reason why their metallicity is poor is because you see stars are continuously forming. Stars are continuously forming. So if a star has formed recently, then they're forming from material which has been enriched by earlier generations of stars. And because they've been enriched with metals from earlier generations of stars, they are metal rich. Whereas stars which are formed from the primeval material or very early on in the evolution of the galaxy, then there would not be much metals because the metals are synthesized in the interiors of massive stars, and these are sort of put back into the medium by explosions such as supernovae. But before these stars had a chance to form and evolve, if you form stars from primeval material, they will be metal poor. So these two populations of stars were recognized by Walter Baade in 1944, studying some of our neighboring galaxies. But he also mentioned that Jan Wood, the famous Dutch astronomer, had noted similar similar types of stellar populations, the two types of stellar populations, in our own galaxy way back in 1926. Now, to go back to one of your earlier questions, how do we know what the structure of the galaxy is? And how far does it extend? Okay. Now, the way we try to find out the structure of our galaxy is to find out the location of the stellar and the gaseous components of the galaxy, finding the distances and locating them. So as you saw, like William, Herschel, and Herschel's and Kapteyn's universe were very limited. And that was largely because they were sitting somewhere near the sun over here, the Earth would be over here, and the optical observations would limit them to a certain distance over here. Okay, a certain distance over here. And that is why their view of the universe, the view of our galaxy, was limited by the observations possible at the time. Now, if you want to go for deeper, one thing is, of course, bright objects like globular clusters. Because they're bright, they can be seen further away. And because they're also away from the disk of the galaxy, that they would suffer less absorption and extinction because the dust is located in the disk of the galaxy. So by looking at the locations of this, by identifying these sources, if you're imaging this, making this image at infrared wavelengths, you'll be able to see further. If you do it at radio wavelengths, you'll be able to see even further. And it is by looking at the concentrations of these various gaseous and stellar components that we reconstruct the structure of our galaxy. Which is a disk with spiral arms. You can see that the two main arms, the Scutum Centaurus arm and the Perseus arm, and they're attached to a central bar over here. There are two minor arms, the Norma arm and the Sagittarius arm over here. Let me point it out. This is the Sagittarius arm over here. This is the Norma arm. And you can see the major arms are attached to the end of the bars over here. There's also an outer arm. There's something called a far 3 kiloparsec arm, which is identified from radio observations. And the sun is located in what is called the Orion spur or the Orion arm. Okay. So this is the broad structure of the disk of our galaxy. In external galaxies, you can see them more clearly, because you can see them face on. If you see them face on, you can see them clearly. But in our galaxy, we are sitting inside, so we got to reconstruct it from the observations which you can make by sitting on the Earth. Just to remind you of galactic coordinate system, because we will come to that in a short while, that the galactic coordinate system is centered on the Sun, 0 to 90 degrees, 90 to 180, 180 to 70 to 70 to 360. These are the galactic longitudes. And if you go north or south, you'll come to the galactic latitudes over here. Okay, so this just reproduces what we have talked about so far and shows you an image of a globular cluster. So these are the main components we talked about. This is from a famous song by Monty Python called the Galaxy Song. The scales are roughly right. And what we have not talked about so far is a dark matter halo, which I put in italics over there. We'll come to that in a very short while. So these are the basic components that we have talked about so far. And we are over here. We're sitting over here. All right. Now, just to give you a quick preview of the different components, approximately circular disk of stars is a disk which rotate about the center of the galaxy. Luminosities, I'll share these things with you, so don't try to remember these right now. I've listed over here the luminosity of the disk and the mass of the disk, and this extends to about 15 kiloparsec from the center of the galaxy. Okay, 30 kiloparsec in diameter. So there is no sharp boundary to the galaxy. All right, and density falls off exponentially, so you can take the scale height if you want to. But what people often do in looking at sizes of galaxies, they measure the size to a certain brightness limit. So maybe 25 magnitude per arcsecond squared or so. Holmberg defined it in terms of a blue magnitude, and is called a Holmberg radius, but there is no sharp boundary. And what was done by Holmberg was from the B light, the visible light. But when you look at the radio frequencies, for example, you might find that neutral clouds extend far beyond the optical extent of the galaxy. And today we'll see in a short while that a dark matter halo extends far beyond what you can see at optical wavelengths. So the disk consists of a thin disk with a 300 parsec height and also a thick disk, which is about a 1 kiloparsec height. The thin disk contains most of the stars' molecular clouds, and that is where star formation is taking place. When you come to the bulge, it's a spheroidal component at the center of the galaxy. Yogesh is asking, do all spiral galaxies have these 4 arms? No, it varies from galaxy to galaxy, right? It varies from, this is our galaxy. In our galaxy, we have been able to map it with far greater detail because it's close by, although we are limited by being inside it, but this can vary from galaxy to galaxy, right? The center of the galaxy, as we saw, was about 8 kiloparsec, 8.5 kiloparsecs away from the sun. The bulge consists largely of old stars, and it is formed at the galaxy's potential width. Today, we know that the mass of the bulge, as determined by the stellar velocity dispersion, is related very closely to the mass of the supermassive black hole, which is sitting inside it. And the bar is an ellipsoidal component superposed on the bulge. And these bars are due to dynamical effects. Stellar orbits which deviate from circular orbits, they elongate and form these bar structures. And bars are temporary structures. Even we'll see in a short while that the spiral structures are also transient features compared to the lifetime of the galaxy itself. Then we talked about the halo, and we talked about the halo gas as well. All right. And the halo we mentioned consists of largely old metal poor stars. We'll come to about the dark matter halo in a short while, but that contains about 80 to 90% of the total mass, nature not known, and this probably has to do with the initial fluctuations in the evolution of the universe from which our galaxy itself evolved. I've just given you one example over here to see how the stellar halo may consist of old metal poor stars drift apart from a dwarf galaxy. There's a citizen science project called Milky Way at Home, and this was a discovery by Heidi Newberg, who found that there was a concentration of stars in a certain direction, and later it was followed up and shown to be most likely the remnants of a tightly disrupted dwarf galaxy. The bottom picture shows simulations of what you will see, and the upper picture shows you the wedge which has been identified of an increase in stellar density due to tidal disruption of a Sagittarius dwarf galaxy which is orbiting about our galaxy. So when you look at our galaxy, for example, in neutral atomic hydrogen, you find lots of evidences of tidally disturbed, tidally sort of trip gas, as well as gas which may have been left over from when the galaxy formed, as well as gas which may have been ejected out from our galaxy by supernova remnants, which may have formed, bubbles leading to galactic fountains. So you can see that it's a very rich environment. It's a very rich area of study to try and look at some of these aspects in greater detail. I'm just sort of trying to introduce you to a little bit of it over here. So um, I'll not spend too much time on this. It shows our galaxy, largely the galactic disk at different wavelengths, right from radio continuum to neutral atomic hydrogen to radio continuum at high frequencies, which you can see has a smaller scale height compared to at low frequencies. Then infrared emission, optical emission, X-ray emission, where low energy X-rays can also get absorbed. And then there is the high energy gamma ray emission. The radio emission which you see is due to synchrotron emission, which is due to highly relativistic particles emitted by the synchrotron, by the highly energetic electron gyrating in the magnetic field of our galaxy. So there are a couple of questions in the chat. So let me just address that. What does bulge contains? Are the halo and the bulge the same, or the halo is part of the bulge? Okay. So as I mentioned a little while earlier, that the bulge consists of these old stars. Okay. This is the bulge over here. This is the bulge over here. Okay. A spheroidal component in the center of the galaxy. Okay. About 8 kiloparsecs from the sun. And this largely contains the original stellar population, although there are some young stars as well. And the halo is much larger than that. Okay. The halo extends much beyond that. Okay. So halo consists almost entirely of old stars, but it is on a larger scale than the bulge, which is attached to this. So bulge is like a ball put in the middle of a chapati, whereas a halo extends much larger distances than what the bulge, which is shown over here. I actually had a picture of the halo as well a little while earlier, isn't it? This is the halo. You can see the halo is much larger and the bulge is smaller over here. All right. They will contain old stars largely, but the general components of the interstellar medium, which we talked about earlier. Okay. Now, we know a lot about the magnetic field of our galaxy, but I'm just showing you magnetic fields directions in two spiral galaxies, outside our own, because you can image them very clearly with radio telescopes. And these little vectors which you see are directions of the magnetic field. So largely along the disk of the galaxy, but they're also orthogonal to the disk of the galaxy, which gives rise to these halos in these galaxies, which is also prevalent in a lot of our galaxies. A lot of these spiral galaxies, which we can see edge on, you can detect these halos very beautifully. I'll keep an eye on the time. Let me see, where am I? I'm very close to 11 now. Maybe I'll just take about 10 minutes more, and I'll tell you a couple of important things regarding our galaxy. I've shown you neutral atomic hydrogen over here and carbon monoxide over here. This is the one where which is you can see is thinner, has a smaller scale height. This is denser, as we saw when you look at the components of the interstellar medium, and this is where stars are forming. Okay, neutral hydrogen clouds are warmer, but they are very important because they pervade the galaxy, and we can study the dynamics of the galaxy using both neutral hydrogen and CO. But hydrogen is much more prevalent, and it's the most abundant element in the universe, and we can infer a lot about the dynamics of our galaxy by looking at the H1. Now we looked at the different components. How do they move? The stars have random velocities. All stars have random velocities, and they're in tens of kilometers per second. But the stars in the disk are moving around, not perfectly circular, but roughly circular around the center of our galaxy at a velocity of about 220 kilometers per second. Now, in the bulge, which is shown by red over here, as well as the halo, which you can see is larger, they move about in largely random orbits. Okay, largely random orbits. This is the way we have found from observations the way that dynamically the dynamical components or dynamics of different components for galaxy. Now, if we look at the star, if we look at our planetary motion, for example, the planets, they follow Kepler's laws of motion and would actually decrease as 1 upon square root of r, right? 1 upon square root of r, and this is what you see from Kepler's laws of motion. Now you can go and try and model that and see what you might expect from motions of gas or stars in our galaxy. What velocities are they moving up? When I said 220 kilometers per second, that is the average velocity at large distances. But what would you expect if they were moving according to Kepler's motion? In the case of the solar system, almost all the mass is concentrated in the sun, but that's not true of the galaxy. It's distributed out in the disk. So you can try and model that. And this is what you would expect, the blue line over here, from the distribution of light in the disk as well as the bulge of the galaxy, right? Now, what you observe is very different. You get much higher velocities, and we shall see how that leads to the conclusion that there is dark matter in our galaxy, okay, whose orbital velocity you can see increases, whose contribution to orbital velocity increases with distance from the center of the galaxy. So it has a gravitational influence, and that is what we can infer from radio observations. Okay, now these are observed rotation curves, these are actual points. Okay, the red line actually is just a rough fit to the points. There are larger errors over here compared to over here. There are wiggles, responding to different gravitational potentials. The sun is over here, but you can see that around the sun, at large distances, it is about on the order of 220 kilometers per second. I mean, there are variations, so don't pick up a fight if somebody gives a slightly different value. But basically, it doesn't come down like Keplerian motion at all. And that is what has led to existence of dark matter or inference of dark matter not only in our galaxy, but other galaxies as well. So I'll spend the last 10 minutes just elaborating on this a little bit more, and then we will stop and take questions. But if you have questions in between, then do feel free to put it in the chat or raise your hand. But please keep your mics muted if you're not asking a question. Now, if it's a constant velocity, v equal to r omega, if v is equal to constant, then r would be inversely proportional to 1 upon omega, or omega would be inversely proportional to 1 upon r. So you can see that as you go closer to the center, the angular velocity would be larger. So inner orbits will pull ahead and the outer orbits will lag behind. A slightly more detailed calculation, you will see that the parallel component of the velocity of a cloud, which you will measure, will depend upon the angular velocity at that distances which you're looking at, minus the angular velocity at which you're going around the sun, you're going around the center of the galaxy, which means angular velocity which the sun is going around the center of the galaxy. So if omega r is equal to omega r sun, that means a circle which is which has the same radius as that of the sun, then you will not measure a parallel component of velocity. If it is inner, for example, omega r is larger as we saw over here, then v parallel will be a positive component. When you go to beyond the solar orbit, then omega r would be less than omega r sun, and you would be actually approaching the clouds, and it will tend to have a negative velocity. Keep falling into different. Okay, Subrata Sarangi has asked the question. We'll come to that in a little while. Okay, so using that, we can try and infer the motion of the galaxy. So what I have mentioned earlier, in a short lecture, I can't get into derivation of this, but you can see that this is the line of sight towards you. Okay, this has the maximum velocity over here. All right, so and its velocity is actually much larger than that of the sun. Okay, the angular velocity over here. So what you will find is that 2 will occur at the largest component of parallel velocity. When you cut lines of sight which are further away from the center, you will find velocities which are smaller. Located at nearby clouds or in the circle, you'll find 4, that is over here, plus local gas. And if you go beyond this circle, then actually the sun is moving faster than this. So it will appear to approach you. So what we have is, okay, I'll just put on the batteries. Okay. Now, so what you'll see is that it'll tend to approach you. So once it's approaching you, you'll get a negative velocity. Now, this is another interesting way of trying to look at the structure of the galaxy, because where the arms are, you will be able to have the highest intensity because that's where the gas is more prevalent. And you can also try and model this and try and reconstruct and see how the gas is distributed, as well as measure the velocities. Too much of detail I'll not get into, but will you all please learn to mute your mics? Okay. If you're not asking a question, this is the third or fourth or fifth time I'm repeating it. You're either students or teachers, and if you cannot follow a simple instruction, it is extremely sad. Okay. This is the end time. Sagar has also asked you, and yet you cannot keep your mics muted if you're not asking a question. Is it a very difficult thing to do? I mean, have courtesy for others, right? There are many others listening to this talk. Okay. Now let me try and just give you a little bit of mathematics to try and illustrate how the dark matter comes about, and then we will close today. Stars and gas moving in roughly circular orbits with velocity vr, and we said the random component is much smaller than the circular velocity at which is moving. Notice the z component is mentioned over here, but we saw that the random velocities are about 10 kilometers per second, whereas the circular motion is about 220 kilometers per second. I will just look at Kepler's laws, okay? Now, acceleration of a star moving in a circular orbit must be balanced by the force of gravity. This is something which you know very well. And if I put mr as a constant density, if density is constant, then mr would be 4 third pi r cube rho, so that the mass enclosed within radius r would keep increasing with distance. And if you plug this in over here, then you'll get velocity r is equal to 4 pi g rho by 3 r, okay? Because r cubed will cancel with r squared, it will give you r, and from this bottom r, you'll get r squared. When you take the square root, you'll get r. So if you look at our galaxy rotation curve, which I showed you earlier, that at the central region, it seems to go up as a solid body rotation. So such a thing can explain, distribution would be able to account for VR proportional to R, but it definitely cannot explain the flat rotation curve. So to explain a flat rotation curve, we have to look at other density distributions. Again, going back, suppose we consider a density profile. Rho r is equal to rho 0, r upon r0 to the power of minus alpha. R0 is just a scale factor over here. These are just normalizing units. At alpha less than 3, you can work out dmr is equal to 4 pi r squared rho r dr integrated, and you will come to this expression. Vr, these are all constants over here, is proportional to r to the power of 1 minus alpha by 2. Now you can see straight away over here that if I put alpha equal to 2, I'll get 1 minus 1 is 0. So Vr is equal to a constant. Okay, implies alpha equal to 2. If I put it over here, it implies that rho r varies as r to the power of minus r2, singular isothermal sphere. But how does the mass increase? You'll find that the mass, when you express it as dmr is equal to 4 pi r squared rho r dr and integrate, r to the power of 3 minus alpha. So R would be proportional, MR would be proportional to R. But the thing is that mass cannot keep increasing indefinitely, right? And this kind of, I'm just giving you an idea of how one might get a flat rotation curve, but this is not based on any cosmological simulations of how galaxies and structures formed. And there are density distributions which are inspired or which are lead from distributions of dark matter from n-body simulations, and Navarro, Frank, and White is one such profile. But these are profiles which will give you a flat rotation curve, and also rooted in our cosmological understanding of how galaxies may have formed. But what you do need is matter, which you cannot see in visible light or in any part of the electromagnetic spectrum. This is what is referred to as dark matter. So all our galaxies are embedded in dark matter halos, and from the rotation that you measure And from Kepler's laws, I'm putting a very rough estimate. This is about 10 to the power of 11 solar masses is what you get as a mass, which is about a factor of 2 larger than the total mass in stars and gas within this range. But this is larger because it hasn't taken account of it has to take account of the dark matter as well. So going back, the dark matter density is required to have this form to try and explain a rotation curve of this shape. And almost all galaxies that we measure have a flat rotation curve. So this is what our Milky Way looks like, right? The Milky Way's total mass is about 5 into 10 to the power of 11 solar masses, and more than 80% of this matter, or roughly about 80% of this matter, is in dark matter. So we are in a very nondescript part of our galaxy, which is visible, which is detectable in visible light, or in any part of the electromagnetic spectrum, as we saw. And this is the bulge over here. It appears slightly flattened than it should have been probably. And then the red dots, which you can see, is the halo of the galaxy, where you get the old stars, the old stellar populations. But all this is buried in a dark matter halo, which contributes about 80 to 90% of the mass of the galaxy. Okay. I think I'm probably running out of time, so I'll probably stop here. But one of the interesting things about our galaxy are the spiral arms. What are they? And that relates to one of the questions which was being asked about stars moving in and out of the galaxy. Now, we saw that the disk is differentially rotating. So differential rotation itself is not responsible for the spiral arms, because if you let a differentially rotating disk be responsible for it, then the spiral arms will be very tightly wound, very unlike what we see. So these spiral arms are believed to be due to density waves, where there is increased density of matter due to responding to the potential in the galaxy itself. And this is what gives rise to the spiral arms, which we see. And actually, the old stars may move in and out of the galaxy. This is one of the questions which was being asked. That the galaxies are the spiral arms are actually much shorter lived. They are not rigid structures, as Subrata Sarangi had asked. But is there any evidence that the stars, as they orbit the center, keep falling into the different arms? The answer is from the time scales which we infer, we know that they can move in and out, but the velocities and the time scales which we can estimate, time scales is just too long to follow individual star and see where it is going in and out of the arm. But given the time scales of motions and the possible time scales of the arms, they can move in and out of the galaxy, and that is what the spiral arms are locations where the stellar orbits of such as stars are more densely packed. Gas is compressed, generating new stars. Arms rotate at a pattern speed which is not equal to the circular velocity. Long-lived stars enter and leave the spiral arms. So these are estimates from our understanding of the time scales involved. And just to give you a rough idea that if there are orbits which are perturbed, which are not all circular over here, you'll see that there is a greater density along certain directions. And these are the waves where once there's an increased density, there will be increased gravity, more matter will fall into it. But these are again transient phenomena compared to the lifetime of the galaxy. The last major component is obviously the central black hole. This is a radio image, a stunning radio image of the central black hole of our galaxy, which consists of very dense star clusters, a lot of phenomena taking place, some due to the massive black hole itself, and some due to intense bursts of star formation. There are dense star clusters over there with very heavy stars, 50 to 100 solar masses or so. And some of these would explode as supernovae, form relativistic bubbles, and fumes of hot gas will be emitted from the central region of the galaxy. And one of the most striking examples of that is the Fermi bubble, which goes up about 25,000 light years. Fermi is a gamma ray telescope, and so this has been detected in gamma rays. And it is believed that this is possibly due to activities in the central black hole, which, as you know, is about 3 million solar masses or so. Heavier black holes probably give rise to jets, but some of these low mass black holes in less active galaxies could give rise to these bubbles. It may be more difficult to detect in more distant galaxies, but it's a beautiful example of high energy gas emitting at the highest energies possible, um, escaping around the minor axis of the galaxy, perpendicular disk of the galaxy, giving rise to high energy emissions. And this is possibly related to the black hole, which, as you know, was discovered by, whose mass was estimated by following the motions of stars in the center of our galaxy. This is some absolutely stunning work which has been done by Andrea Ghez and Reinhard Genzel, and you may have heard a lot about it. S02 is the one where one complete orbit has been completed, and by modeling this, one has been able to estimate the mass of the central black hole, which is close to about 4 million solar masses. So I'll leave you with just pictures of Andrea Ghez and Reinhard Genzel, who got the Nobel Prize in 2020 for this work, and just a three-dimensional simulation of this. It is going, yeah, of this from Andrea Gez's website. Absolutely beautiful work, and as we mentioned, that it's very difficult to see far in the optical light. So these are cool stars, and these observations have been made at larger wavelengths using active optics, adaptive optics, so that you get almost diffraction limited resolution, high resolution, to be able to follow the motions of these individual stars. So I'll leave you with this. We'll end over here. We can take a few questions, although you have asked questions in between, which is excellent. I probably addressed Subrata's question in the chat. Keep falling into the answer. Okay, that has been addressed. Okay, any other questions? You can raise your hand, unmute yourself, or put it in the chat, whichever is convenient. Any further questions? No? Okay, there's one question. We'll take that. Collisions of galaxies you started but didn't continue. If galaxies collide, what type of collision will it be? Okay, actually, I didn't want to talk about collisions of galaxies today, but you see, galaxies occur in groups. Okay, in groups and clusters of galaxies. Some maybe loose groups of just dozens of galaxies. There could be rich clusters of thousands of galaxies, and galaxies move around responding to the potential in which it is moving. And in the course of this motion, galaxies of equal mass can collide. Smaller galaxies can fall into the potential of the larger galaxy, and when these galaxies collide, the interstellar medium compresses the galaxies, compresses the gas in the galaxies, leading to bursts of star formation. And we find that these galaxies can have all kinds of properties after they collide. You can actually catch them. Catch different systems in different stages of collision, where you see huge tidal arms which have been stripped apart. If you just Google and find out galaxy collisions, you'll see a lot of images of it. You'll find evidence of star formation. You'll also notice that these collisions are probably far more prevalent in the early evolution of the universe. And also simulations and following different collisions at different stages show that spiral galaxies, at least some of them, may merge to form elliptical galaxies. Gas is heated up, expelled, and the stars settle down to an elliptical shape. So these are some of the interesting manifestations of the collisions of galaxies. They happen when galaxies are in groups and clusters. I showed you an example where the Milky Way itself has torn apart a tidal galaxy, but this will keep happening in other galaxies as well. One of the many examples is very sort of razor-shaped galaxy, which I don't have a picture of right now, but there are many such examples. Now, okay, but which observations lead to spiral arms of the galaxy? The spiral arms of the galaxy can be found by looking at the positions of stars, positions of gas, positions of objects like pulsars, positions of regions of ionized hydrogen, the O and B stars which are forming, which are the most massive stars, which are small ages, are located in the spiral arms of galaxies, looking at the locations of molecular arms. So you need to identify these objects and get an estimate of their distances. And also, as I mentioned earlier, looking at the neutral hydrogen gas, where the maximum velocities occur, where the peaks in intensity occur, you can go and infer where the spiral arms are. So from observations of different kinds of objects, the gaseous, stellar, star-forming, nebulae, etc., one tries to reconstruct the spiral arms and how they are located in our galaxy. Is that okay, Amit? Okay. Now, Amit Kumar Pandey says, please clear me about difference between space and interstellar space. Okay. Interstellar space is a space between galaxies. Okay. Interstellar space. Okay. When I say interstellar medium or interstellar space, interstellar medium is a space between galaxies. When I say when I say intergalactic medium, I mean the medium between galaxies. When I say intra-cluster medium, I mean the medium within groups or clusters of galaxies. When I say interplanetary medium, I mean between the medium in our own solar system, the space between the planets and the sun. Okay, so space is everywhere, right? So time and space are where we are located, but different parts of that space go by different names depending upon what you're studying. Okay, is that clear, Amit Kumar? Okay, you're muted, but you can. Okay, you responded. Okay. Now, Subrata, you have one second. Let me see if I can ask to unmute. I can't unmute you, so can you put your question in the chat, Subrata? Because I think you also had your mic on, so everybody has been muted now. Thanks to that.
No, sir, good morning. No, I did not have my mic on. Anyway, sir, am I audible now, sir?
You're audible. You're audible.
Okay, sir. I was wondering about that those arms and it's an extension to that question which I just asked about the rigid structure. It not being rigid structure, but the stars keep falling in and out. I was extending. I was thinking if the stars keep falling in and out of the star of the arms, then we should observe the blank areas or the dark areas between the arms which we observe should also contain stars. I mean bright stars, because stars keep on going out and into the arms, but we don't see them. The arms, the space between the arms are reasonably dark. But that may happen if there is some kind of correlation between the stars rotational speed, so that with a certain rotational speed all the bright stars go out of one arm and then get into another arm, so the arms keep looking bright.
No. That's not the way to think about it. Now, I'll ask you a simple question to start off with. What are the bright stars? Which stars are the brightest?
The OB type stars.
The OB type stars. Yes, the OB type stars are the brightest stars. Yes, and they are also the shortest lived stars, right? They live for millions of years, whereas stars like our sun live for billions of years, and also younger stars will live, low mass stars will be live even longer. Okay. Now the thing is that the spiral arms they are bright. Not only is it stellar density large, but they are the ones where the stars are forming. So they consist of the brightest stars. The inter-arm region is not where stars are formed. So the old stars which are moving about may move in and out of the stars, but the O and B stars will be largely within the spiral arms of a galaxy. Okay. Okay. So the brightness is one is a contribution of the density of stars, but the other is where the stars are forming, because the molecular clouds from which the stars are forming are located in the spiral arms of the galaxy. Okay.
Yes.
Okay, and I'm sorry if I sort of wrongly accused you of unmuting yourself. Because somebody sort of put something on the chat which I saw, but anyway.
Yeah.
Okay, thanks very much.
Thank you.
Thank you. Any other question? We'll take one last question and we'll stop.
Sir, our galaxy has a supermassive black hole in the core. Yes. And also there is a lot of radio emissions, this gamma ray bursts, etc. are also found in our galaxy. but still it is not regarded as a radio galaxy or active galaxy.
Yes.
In its evolutionary stage, once will it become a radio galaxy or a active galaxy or something like that?
Okay, that's a very interesting question. So let me elaborate on that a little bit, and then we will stop because I think the next speaker will want to come soon. Okay, see when you call
Sir,
a radio, yeah.
Sir, could you please repeat the question? I mean, I just missed that. What is the question? Because you said that it is interesting. So,
Okay, okay. So the question that is being asked is that that our galaxy also has a supermassive black hole, but it is not considered to be a luminous radio galaxy. Will our galaxy one day become a luminous radio galaxy? Okay. Now, luminous radio galaxies are usually at least a couple of orders more luminous than our own Milky Way galaxy. Okay. Now, the thing is that when we look at the question as to what creates or what is responsible for such large luminous radio galaxies, then we find we are not yet sure what causes it. But one thing we know is that almost all of them, with just a handful of exceptions, are associated with elliptical galaxies. But not all elliptical galaxies are luminous radio galaxies. Only about 10% of them are radio galaxies. So there are speculations that maybe every galaxy goes through such a phase, but the answer is not clear at all. Now, you can ask yourself the question, what triggers radio galaxy? Now, initially people thought that it may be the mass of the black hole. Because when you look at the mass of the black hole, then you find that our galaxy is about 4 million solar masses. But the luminous radio galaxies and quasars are of the order of 10 to the power of 8 solar masses or thereabouts or larger. So the mass of the black hole may play a role. But then there were also such massive black holes in elliptical galaxies which are not radio loud. So then people speculated that maybe spin also plays a role, that you need a maximally rotating black hole. And as we saw in our lectures on AGN, that the efficiency is much more. Kerr black hole is a 0.42 efficiency. But then people found that also low luminosity non-radio galaxies or non-radio loud galaxies had maximally rotating spinning black holes in a couple of Seyferts and Seyfert galaxies. So then it's probably a combination of both spin as well as mass, which is these luminous radio galaxies. They are much more massive than these galaxies, plus also availability of fuel. But in addition to that, if there are any other factors playing a role in terms of, for example, you heard about the different accretion phases in black hole binaries, we don't really know the answer. But our galaxy will not evolve into a radio galaxy. The mass of the black hole is too small to be able to get into a powerful radio galaxy. And as you can see, it's not even forming a jet. Galaxies which are more massive than about 10 to the power of 6.5 solar masses, from a detailed study which Ranieri Baldi and we had done together, Ranieri Baldi led effort, found that they can have small jets, but they're not like radio galaxy jets. Our galaxy doesn't even come to that category. So our galaxy will not become a radio galaxy. And to form a radio galaxy, probably we need more massive black holes, maximal rotation, spin, rotating spin plus availability of fuel, plus perhaps other factors which we are not very clear about. Okay, so we'll end at that because I'm sorry I'm running to the next speaker's time, and we will stop over here. But if you have any further questions, you can put it on you can email me or put it in the Moodle platform, Slack platform, and I'll try to address it. Okay. So we will stop here, and thanks very much. I'm sorry I overran a little bit. And I'm sorry also I berated some of you for unmuting yourself while not speaking, but all the very best, and thank you very much.
Thank you very much, Professor Saikia.
You're welcome. Thank you very much.